All right, hopefully you found the recording, and those of you that were with me last year, you're well used to this situation and what we're doing here. And those of you that you're brand new, uh, welcome, and hopefully you'll get used to watching the videos and then coming back in class tomorrow and me helping you with your homework. All right, this is Algebra 1, Lesson 1.1, Sets of Numbers. All right, so let's get rolling here. What is a set? A set is simply a group or collection of objects. A group or collection of objects. It's a group of things. It's a collection of things. All right, a set. Not a big deal. We would have talked about this some last year in pre-algebra. All right, some terminology here. I'm going to use my black. Each element of a set, each item of a set is called an element. You can also call it an object. So the things inside the set are the elements or the objects, okay? What's inside the set called elements or objects. Now be careful here because you have to remember whenever you're going to list the members, the elements, the objects of a set, you have to put them inside of braces. Braces. So the elements of sets are listed inside of braces. Don't forget that. Students forget that and you lose points. You know, math, it's a you got to be technical, and so you have to have your all of your protocols properly done. So be careful there, all right? You need braces, and you can notice my two example sets here below have braces. The first set is a finite set. What does that mean, finite? Well, finite means that it has a definite number of objects. All right, and if you look, there are 1, 2, 3, 4, 5 objects, right? So you got 5 objects there in that set. It's a finite set. There's 5 objects. You look on the right, however, it's an infinite set. And you'll always know it's an infinite set by the ellipses. 3 dots in a row are ellipses. Now, let me just take a brief moment and mention when to use the ellipses or how to use the ellipses. All right, the ellipses are used to signify that the pattern continues on forever. Now, you have to have 3 numbers in a row with the established pattern before you use the ellipses. That's easy to remember. 3 dots, 3 numbers in a row. All right? So you need 3 numbers in a row in the pattern to use the ellipses. Now, in our infinite set here, all the numbers happen to be in a row. But you could have a set like this. You don't need to write this. You know, you could have 1, 7, and then you could have 9, 10. Well, you can't use ellipses yet. But if you had 11, then you can use your ellipses, because you have 3 numbers in the established pattern and then the 3 ellipses, okay? So a little bit of a technicality there, but that's important. All right, so this set goes on forever, infinite set, not hard to understand. All right, so let's grab our green here and a little bit of symbols. All right, -3 is a member or an element of the set K. Is that correct? All right, well, here's the is an element symbol. It's kind of like an E, but it's curved. It's a curved E. Now, sometimes, depending upon how any certain font is, it may look a little different, right? And you're used to fonts. We're in a computer age. All right, and what is this saying in words? -3 is an element, filling in the blanks here, of set K. And that's how you'd say that in words. Of course, if you guys remember last year, the idea of negation. So look at 5 and look at set J. Is 5 a member of set J? And 5 is not a member of set J. So I'm going to do my is a member symbol. I'm going to take my red and I'm going to negate it. And we learned how to negate last year, right? So 5 is not an element of set J. 5 is not an element of set J. How about a set with no elements? Kind of boring, but it does come up, and so we do have to deal with it. A set with no elements is called, has 2 names. You can call it the null set, null, N-U-L-L, or you can call it the empty set, the null set or the empty set. It's simply a set with nothing in it. What is the symbol for the null set? It's the 0 with the line through it. Pretty universal symbol these days. You see the line through it. If you're in Europe and you're driving, you'll see a lot of signs with lines through them. The empty set, 2 braces with nothing in it, right? Oh, okay, good. It's empty. That's pretty obvious, right? So null set, 0 with the line through it, empty set, the two braces. Let's get into the aspect of using sets. All right, let's use the sets here. All right, so I've got 3 examples, set H, set J, and set L. Notice that the sets are in braces, right? Set H is finite or infinite. And hopefully you're thinking it is finite. Set J, finite or infinite. Hopefully you're saying infinite. Set L is finite. All right, you have to take that in mind. I'm going to use my red here. So the first operation we want to look at is union. Union. Union's easy. Union, you put things together, right? You union something. Oh, dearly beloved, we are gathered this day to witness in holy matrimony, blah, blah, blah. You know, this guy and this girl. Union, putting together. And that's the aspect. The symbol looks like a U. Does not have any tail, though, or anything like that. Again, depending upon the font, it may look a little different. But it's basically a U, and that is a symbol for union. What is union of two sets is all members that belong to either set. You simply list all the members that belong to either set. So we're going to take set H, take your union symbol in red, stick it between them. We're going to union set H and set L. Okay, so the best way to do this is to list everything in numerical order. So I'm going to look at set H, and I'm going to go the -2, the -1, the 0. Now notice this. Set H has a 1, and set L has a 1. That's the same number. You don't list the same thing twice. So when we're putting these two together, we're only going to list that 1 once. Okay? So I have the 1. Set H has a 2. They both have a 3. All right. Now I'm going to go to set L, get its 5 in there, get its 7 in there, go back to set H and get the 12 and brace. Now remember, this is a video, so you can pause at any time that you need to catch up or if I'm going too fast for you, or you can even rewind and go back if you need a further explanation or you missed the explanation. All right, so that's H union L. Now, look at what happens here with H union J. I'm just going to start out similar. I'm going to start with H because it has the smallest number in it, -2, -1. They both have 0. H has a 1. They both have 2. H has a 3, right? Now I'm in J. J has a 4. J has a 6. J has an 8. What else does J have? Be careful here. Doesn't J have a 10? Yes. Do they both have a 12? They do. And quite honestly, technically, I could have stopped a little earlier because I see the pattern. See the pattern since the 4, 4, 6, 8? I could have used 4, 6, 8, ... That'd be a cute way of doing it. I could go 6, 8, 10, ... 8, 10, 12. I'll do my dots here. All of them would be the same answer and would be correct. Technically, this isn't quite simplified, but it's very illustrative, and therefore we're fine with that. But be careful with the ellipses. Remember, all those numbers of the ellipse are in the set, and so you got to be careful. So that's the first operation, union. Putting things together should be easy to remember. Remember, do not repeat anything twice. Don't forget your braces. The second operation, and I'm going to take my green here, is the set of intersection. Intersection. You know, you can think of two lines intersecting. So watch, you don't need to draw this in your notes, I just wanting to get you to think here. Look underneath the words all members, look right here. I'm going to take a line. Now what is a line? It's all the points that make up that line. All the points, 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 forever that way, forever that way. Again, you don't need to draw this, I'm just trying to get you to think. I'm going to take a blue and all the points, 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 all the points. It's supposed to be straight, by the way, but you know how hard it is to do electronically. Now, if we were to intersect these two sets, it would be that point right there. Do you see how that point belongs to the green line, but that point also belongs to the blue line? Well, that's intersection. That's intersection. So if you look at our definition, all members that belong to both sets, that's intersection. All right, so that's what we're thinking about here, and that's what we're doing here. Oh, got to get rid of all these dots. All right, we're good. Okay, so what is the symbol for intersection? It's an upside down U. Again, depending upon the font, that will look a little bit differently. Let's go back and let's intersect our sets. So, intersection symbol, H intersect L. Okay, now we're looking for only the numbers that are in both. -2 in both, no. -1 in both, no. 0 in both, no. 1 in both, yes. 2 in both, no. 3 in both, yes. And 12 in both, no. That's it. Only 1 and 3 belong to both. If you want to, pause the video and you can do H intersect J. All right. If you didn't pause, right? Again, I'm looking for what's in both. -2 in J, no. -1 in J, no. 0 in 1 J, yes. Is 1 in J, no. Is 2 in J, yes. 3, no. 12. 12 is in J, right? It's not shown, but it's there, isn't it? And that's the last possibility. And the intersection of H and J is 0 to 12. Now, remember commutative, associative, all that? All right. Are the operations of union and intersection commutative? C-O-M-M-U-T-A-T-I-V-E. All right, this is our first review of these. We'll go through them a lot. We went through them a lot last year. Do you remember what commutative is? It means you can change the what? And hopefully you said you can change the order. So, union. It is the first set union the second set, the same as the second set union the first set. Can you swap your order? Will it still be the same? You can do it with set H and L up above. If you union L and H, do you get the same answer? You do. And you can try, other unions. You'd find out you get the same answer. So for union, it's a yes. How about intersection? For our example here, we have what? H intersect L. H intersect L. Well, what about L intersect H? Well, it doesn't matter. I can start at L. Is there a 1 in H? Yes, include the 1. Is there a 3 in H? Yes, include the 3. Is there a 5 in H? No, don't include the 5. Is there a 7 in H? No, don't include the 7. 1, 3. And the answer is yes. Both union and intersection, both those operations are commutative. All right, let's turn the page. And we've got 3 more example sets, set G, set K, and set M. And all 3 of these sets are what kind of sets? And hopefully you're thinking the word finite. All right, so we have 3 finite sets. Now let me introduce you to another term here, and it's Venn diagram. V-E-N-N, Venn diagram. Venn diagram. All right, a Venn diagram is a picture to illustrate the relationships of sets. So we've got a couple examples here. In example A, we are unioning set G and set K. Now, for time's sake, I already have set G drawn. So inside the blue box becomes, we're going to do the union of G and K. Now, G's already drawn. I have to draw K. I'm going to grab my black, and I'm going to draw K. But before I draw the circle of K, I'm going to look at K and G and see if they have anything in common, because the circle has to include those common numbers. And look, they both have a 1. That's all they have in common is a 1. So watch now. Here's what I'm going to do. When I draw circle K, I'm going to draw it around that number 1, because remember, we don't list any numbers twice, right? Okay, now the remaining numbers of K have to go in this circle. So I'll put a 0, a 2, an 8, and a 10. There are all the numbers of K. All right, so now, remember, we're asked to do the operation of union. What is union? Union is put together. You must shade the union. Shade the union. Your shading is the solution. Right now, all we did was list the 2 sets. Now, to show the union of the 2 sets, we must shade, and it would be everything in G, also everything in K, and notice that 1 overlaps the 2. And so anything shaded are the numbers that are the solution. the -3, the -1, the 1, the 0, the 2, the 3, the 5, the 8, the 10. Okay? All right, so we're going to do the same thing here with G intersect K. So again, let's draw K, and we just did it. It's going to be drawn the exact same way. See, whether you're intersecting or unioning, that's the same. Only, again, shade the solution, shade the intersection. I'm going to abbreviate for time's sake. Shade the intersection. And take your green now and shade where they intersect. Now, do you see how easy it is to tell intersection and union when you shade? Sure. And so that's easy to illustrate. 1 is the only number that those two sets had in common. All right, so here now, M and M, what's that symbol? Union and intersect. Hopefully you think intersect. So we need to do M intersect G. All right, I want you to pause the video and go ahead and do it yourself, and then I'll come back, all right? But if you don't pause, I'm just going to keep going. All right, here we go. So M, take my black here, 1, 3, 5, 7. I'm already looking at G, right? 1, 3, and 5. Oh, they both have 1, 3, 5. See, I'm going to put that over to the right so I can catch it with my other one. All right, so M, 1, 3, 5. The only other thing is 7, and I have to label it as M. I need a circle for G. It's got to go around that 1, 3, 5. I'm going to label it G. I did the 1, 3, 5. I need the -3 and the -1. And finally, I need to shade the solution, right? And there is the intersection of set M intersecting set G. Okay? Please see how that goes. And again, if you have any questions tomorrow in class, I'll be glad to answer them and get you guys going. All right, grab your blue. Another term here with sets is the term of subsets. Subsets. Do you work with directories in your computer? And you have a main directory and then you have subdirectories, directories under the directory? It's exactly what a subset is, right? Anything in the subdirectory is inside the main directory. That's a subset. Okay? What is the symbol? It's kind of that U on its side with a line under it. Subset symbol. I know it looks like a C. It should look more like a U on its side with the line under. Again, depending upon the font, it'll look a little bit differently. So a set is a subset of another set if every element of the first set of that set that you're wondering is it a subset is contained in the second set. Right? Again, think about your analogy with your computer and your files. Once you click on a file folder, if you have another folder in that file, everything in that folder is in the bigger folder, the upper folder. All right. The idea of subset. I need to get rid of my shade so I can extend this up. All right, so subset, a set is a subset of another set if every element of the first set is also contained in the second set. All right, we got 3 examples. Set A, finite or infinite, finite, B, finite, and C, infinite. All right. Is A a subset of B? So this is a yes-no answer. Is everything in A in B? Is there a 1, 3, 5 in B? There is a 1, 3, 5? Yes. See how this goes? All right. B, is A a subset of C? Is everything in A in C? There's a 1, 3, 5, 1, 2, 3, 4, 5, 6, 7, 8, 9. Yes. Yes. Okay. Notice what happened now. I want you to look at C and look at A. A says, is A a subset of B? C says, is B a subset of A? Hey, you know what we're looking for right now? The idea of commutative. All right, let's look at B. Is every member of B in A? Is 0 in A? No. Oh, well, that's it. We don't even have to look any further. If one thing's not in the other, it's not a subset. And the answer to that one is no. So, is subset commutative? No. Subset is not commutative. All right, last thing, last page here. All right, remember our number system is called the real numbers. Got a little cartoon here for you on the side. The I is saying be rational. Well, the pi symbol is an irrational number. So the I is saying to the irrational number, hey, be rational. But the pi is saying back to the I, hey, get real. Well, I is an imaginary number, not even part of the real numbers, right? Real, imaginary. So that's a little cartoon there. I know you didn't get it. You might by the time you get to Algebra 2. All right, let's go through and look at our sets. What we want to do here now is I have all the sets listed of our real numbers, and I just realized I need to make this a whole lot smaller so I can get all of this in on the same page. So let me do that here momentarily. Let's see. I need my pick. Got to get, that's what I need right there. Okay, come on. I got to make this pretty small so it'll all show on one page. Okay, that's good enough. Okay, so if you take a look at it, we're going to look at all these sets. All right, so I'm going to take my black or your blue, it doesn't really matter. What are the natural numbers? Notice the natural numbers is the small circle in the center, most exclusive. The natural numbers, we're going to use a brace. What is it? It's the set that starts with 1, 2, 3, dot, dot, dot. Natural numbers. 4, 5, 6, 7, 8, 9, 10, etc. Forever it's infinite. 1, 2, 3. All right, natural numbers. Next, we take the natural numbers. We're going to add one more member, and that's the 0. I like to tell students the whole numbers include the whole, the 0. And then 1, 2, 3, dot, dot, dot. So everything, it's just got one other member. By the way, are the natural numbers a subset of the whole numbers? Absolutely. Notice the natural numbers are completely inside the circle of the whole numbers, right? All right, integers. Z is the symbol. Integers are negative and positive counting numbers. So we got to go dot, 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 -2, comma, -1, comma, 0, comma, 1, comma, 2, dot, dot, dot. Ellipses go both ways. All right, still an infinite set. Infinite in both directions. Integers. Are the natural numbers a subset of the integers? Yes, because the circle of the n is inside the circle of the z. Are the whole numbers a subset of the integers? Yes, because the whole numbers are inside the z. Are the whole numbers a subset of the natural numbers? No, because the circle of the w is not in the circle of the n. Again, you can go back and look at this again later after we're done. Rational numbers. Q is the symbol. It's just the way it goes. Rational numbers, basically, it's easier to give a description. They are all fractions, or any number that can be a fraction. So you might think of the number 8 as, okay, well, that's just a regular number, but technically it can be a fraction for 8 over 1. That's why any natural number is also a member of the integers, okay? But it's all fractions, 3/4, 1/8, 1/32, etc. All fractions. And then finally, the irrational numbers. And what are the irrational numbers? Irrational numbers are all non-fractions. Non-fractions. All right, how do you recognize them? You'll need to write this because you won't be able to recognize them without it. What are all the non-fractions? Okay, a non-fraction is all non-repeating, non-terminating decimals. All non-repeating, non-terminating, non-repeating, non-terminating decimals. Okay, if it doesn't repeat, if it doesn't terminate, it's irrational. Let me give you a couple examples. A lot of square roots are irrational. Square root of 2. Square root of 2. Okay. Square root of 5. There's a couple others. Pi, right, from our illustration up there is irrational. 3.1416, and it goes on. It doesn't repeat and it doesn't terminate. Non-repeating, non-terminating, and even the number E. You say E's a letter. E's not a number. E is actually a number, 2.71828, and it goes on. All right, it does not repeat and it does not terminate. We'll learn about E later on in the year. Okay? All right, let's go through now. We want to locate each into the most specific set. Last thing we'll do today. All right. So where do you stick a 5.7? 5.7. All right, it's definitely not irrational because it terminates. It ends at 5.7. Is it a natural number? No. Whole number? No. Integer? No. Is it rational? Is 5.7, can you make it a fraction? You can. It is rational, which is Q, which you're going to put somewhere inside of Q, right? Q is outside of Z inside the blue box. So 5.7. Number 4, most restrictive. Is 4 a rational number? Yes. Is 4 an integer? Yes. Is 4 a whole number? Yes. But is 4 a natural number? Yes. Most specific. It's going to go all the way in N. Get the idea? You can pause if you want to do the rest or stay with me. Square root of 7. Remember, most square roots are irrational. 5/3. Fractions are rational. Again, I could have put it in the left and the right, just outside of Z, inside the blue box. Oh, be careful here. What's the value of square root of 25? The square root of 25 is 5. Oh, that's a natural number. It's kind of disguised. It's got a disguise on. Look out. No, it's just a natural number, right? You got to think simplify. And then negative 11, natural, no. Whole, no. Integer, yes. Negative 11 is an integer. All right, that's the idea. Hey, the homework, remember, will be done in class tomorrow, so don't worry about that tonight. You don't need to do page 5 tonight. That'll be in class tomorrow, and I'll be there to help you. Hey, we're off to a new school year. Hope you're excited. I'm excited. And it's going to be a great year. Lots to learn. I hope you'll work hard. And I hope occasionally when we get to flip the class, it'll be a blessing to you. Have a great night and see you tomorrow in class.